Hello and welcome back. I'm going to, in this particular lecture, talk about nominal variables in a regression model. So till now, we've been doing regression with the independent variables as continuous variables, and for a good reason, since regression talks a lot about variances and the residual sum of squares, the error sum of squares, the model sum of squares. So how do I bring in a nominal variable in regression? So there's a short answer and there's a long answer to that. The short answer is that you cannot bring nominal variables into regression. But that being said, as in data mining and in statistics, no is never a no. The long answer is you can't till you can. And we're going to talk about how can you bring in nominal variables into regression. So one particular caveat that bringing in nominal variables into regression is playing around with the assumptions to a certain extent. So we're going to bend the assumptions of regression to a certain extent. But what we are not going to do, and this is a question which I get asked a lot, is can we assign categories to the nominal variables? So I'm going to talk a little bit about nominal variables. For example, I want to predict variable y as a function of x1, x2, and x3. So x1 and x2 are your normal continuous variables. Pardon my handwriting, but x3 is a categoric variables, which or a nominal variable as we can call it, which has let's say 4 categories. So x3 has 4 categories. So let's say y is the age of a student, and let's say x1 is height of the student, x2 is the weight of the student, and x3 could be, I don't want to use gender, let's use the section of the student. So we've divided students into section, and each student gets divided to section A, B, C, or D. Height and weight, as you know, are continuous variables. So height in centimeters, weight in kilograms or pounds, height in whatever inches, etc. That will also work. And age is also continuous variable in years or months, whichever way we want to capture age. But when I talk about section, I want to bring in section as a variable into a model. Now section or the categories that we have A, B, and C and D, they don't have any direction or magnitude, so I cannot really calculate any variance around section. So variance around the section cannot be calculated. We cannot calculate what is the mean section. So again, mean is also out of the question. We can only calculate the mode section, and frequency statistics are not used in regression that much. So short answer being that section typically cannot be a variable in our model. However, the long answer is, if I really want to bring in section, how do I do that? So some people might suggest, I could code in A as 1, B as 2, C as 3, D as 4, or the other way around, give them just numbers and let them come into the model. That actually doesn't make any sense whatsoever, because if I give them numbers, and we've covered this in our very first lecture, that if I make these as numbers, therefore D minus B is equivalent to, let's say, 4 minus 2, which is equal to 2, and I know D minus B is not equal to B. So this numbering doesn't make any sense. So you cannot give numbers to sections. And if this was an ordinal variable as well, it could be the shirt size of the student, and we are classifying the shirt sizes as small, medium, and large. I still cannot give them numbers. So we can't give them one as small as 1, medium as 2, and large as 3. It doesn't make sense. I might as well give them 10, 20, 30, or 25, 26, 27. What the numbers, by assigning numbers to categories, is not the answer to bringing variables into regression. So before we learn about bringing categorical variables into regression, the one idea that we must literally stamp out right now is that we do not assign random continuous values to the categories in our variable. So you cannot give numbers to the categories. So now, if we can't give numbers to categories and only numbers can come into the regression, how do I bring these variables as how do I bring these categories as independent variables in my model? So this is where we actually use a transformation method, which is also called as one hot encoding, or creating binary variables. So how one hot encoding or binary variables is used is that we actually manage to create a variable for each category and then define that only as a binary category. So presence of a category or non-presence is coded as 1 or 0. So how this actually works? Let's take our HSB2 example in our dataset. So we have HSB2 dataset on which we're doing a lot of our analysis. So here we have HSB2, and I know that race is coded as numbers. So we know that race is coded as per the numbering over there. So Hispanic is 1, Asian is 2, African American is 3, and white is 4. And we've already established that uh, coding them as numbers and using these numbers directly does not change anything. These numbers are still categories and they cannot be brought in directly. So numbers directly cannot be used into the regression model. However, what we can do is for each category in race, I will do a transformation or a transpose and create that many variables. So I know that race as a category has got as a categorical variable has got 4 distinct categories. So can I create 4 distinct variables, and these variables are only going to be binary, yes or no. So for example, for each observation, uh, based on the race of that particular student, we only switch on that particular category. All the other categories are coded to 0. So for example, the first student is Hispanic. So Hispanic column is set as 1. All the other race columns are set as 0. Similarly, for an African American, all other categories are set as 0. African American is set as 1, then white is set as 0. And we follow this procedure. So what happens is now one categoric variable has been converted into 4 different binary variables, and we need to create as many binary variables as there are categories. In fact, the number is 1 less than that, and then I can use these binary variables into my model, and the presence or absence is simply coded as 0 and 1, and that is now assumed to be a continuous variable. Now using this, we can generate an estimate against each of these categories, and basically what that estimate does is now uh, I'm going to just create a new sheet. So when I have a binary variable as a category, so let's say x binary as a category, and this is my dependent variable. So x binary can only be 0 and 1. So when I create a model y is equal to beta naught plus beta 1 into x binary, now x binary can only take two particular values, 0 or 1. So if it is 0, then y is equal to beta naught. If it is equal to 1, then y is simply beta naught plus beta 1, because it's multiplied by 1. X binary is 1, so it becomes only beta naught plus beta 1. So my dependent variable can only take two particular levels, either with the presence or absence. So if the absence of that variable is assumed to be 0, or absence of that condition. So for example, this condition was race, and we are checking whether the student is Hispanic or not. If the student is not Hispanic, the value of y defaults to beta naught, or which is our default value. If the student is Hispanic, the value of y defaults to beta naught plus beta 1. Beta 1 is the estimate against the binary variable, which is Hispanic. And similarly, this is played out for all other categories as well. So while technically I'm still using this as a OLS regression, and prima facie does not appear to violate any of my condition of my assumptions, but using binary variable is stretching it to a little extent, that we are assuming that 1 is greater than 0, and we are plotting Hispanic on a x-axis, with 0 being no Hispanic and 1 being Hispanic, and that gives us a direction over here. So while we can use this to a certain extent, it is not advisable to have too many categoric variables coded in as binary variables in our linear regression model, primarily because it reduces the possible values y can take. So when I bring in this variable, and this is the only variable, then my dependent variable can have only two possible outcomes, which is either y is equal to beta naught or y is equal to beta naught plus beta 1. And when I bring in multiple independent variables with binary categories, so we can actually have we will have a series of permutation combinations, but that will still give us only limited values of y. So while I will be able to capture some variance, it will not be as good as having a continuous variable which can have infinite number of possibilities for y, for infinite number of possible values for x. So even when x is ranging from, let's say, 1 to 10 in a continuous variable, it can take infinite number of values between 1 and 10. It could be 1.1, 1.01, 2.3, 2.03, and so on. So based on these infinite values of x, my y can also take any range of values based on the value of x variable. But when I'm talking about binary variables, it's restricted to these two values only, beta naught and beta naught plus beta 1. And therein lies the problem. While we can bring it in, it's not advisable to have too many categorical variables. The other thing is that if I have a variable which has got 4 categories, so in this case I have variable with 4 categories of 4 races, which is Hispanic, Asian, African American, and white, right? I can create actually 4 binary variables, but I need only, so I'll show you that I need only 3 of them. For example, if I know that the value of Hispanic is 1, right? And then I already know that the student cannot be any of these other races, so they have to be set to 0. Similarly, if I know that the value of Hispanic is 0, the value of Asian is 0, the value of African American is 0, then out of the remaining races, there's only 1 left. So without even looking at the 4th column, I already know the value of white will be 1. Similarly, in the first 3 columns, if I see and if I detect a 1 over here, I already know what the value of the 4th column will be, because the customer is already coded as an African American. The column y of white will be 0. So in fact, by looking at the first 3 columns, I will always be able to guess what is the 4th column's value going to be. We can see that the 4th column is actually it's actually redundant. So I'm just going to write redundant over here. Right? So this column is redundant and we actually don't need it. And if it is redundant, that means this column is a perfect function. So white is a perfect function of Hispanic, Asian, and African American. So what we are saying is, if I know the values of these 3 variables, Hispanic, African American, and Asian, even if it is 0, 0, 0, then I know the value of white is 1. If the value is 1, 0, 0, it will be 0. If it is 0, 1, 0, it will be 0. If it is 0, 0, 1, it will still be 0. So in every case, if I know the values of these 3 variables, I am perfectly able to predict the 4th variable. And now the assumptions of OLS regression tell me that this variable is perfectly explained by the presence of these 3 variables. Therefore, this variable is redundant. I don't need it because the VIF for this will be infinity. This variable is a perfect function of these 3 variables. Therefore, this is a highly collinear variable. Therefore, if I have 4 categories, I only need to create 3 binary variables. If I have 5 categories, I only need to create 4 binary variables. If I have 10 categories, I only need to create 9 binary variables. So depending on the number of categories in my original race variable or whichever categoric variable I need to bring in, I need to check how many categories that variable has. If that variable has got X number of categories, then I need, or N number of categories, then I need only create N minus 1 binary variables to fully capture that particular categoric variable in OLS regression. So this is the procedure with which we can actually bring in a nominal variable into a regression model by using one hot encoding or binary categories. So what we're going to do now is I'm going to give you an example where we are actually convert this race variable in HSB2 dataset and recreate our regression model and see whether bringing in race is actually making a model better or not. So one caveat that every time we bring in a category, that category counts as a variable of its own. And we know if what will happen if we have too many variables in our model. If we get too many variables in our model, we are quite likely to bring in insignificant variables and overfitting can happen. So I'm going to cover overfitting a little later in our next few lectures. In this particular lecture, I'm going to give you an example of bringing in binary variables into a model. And let's look at the HSB2 dataset again. So I have race over here. It's categorized as 1, 2, 3, 4. And I'm going to create a binary variable for this. So let's go down and write the code to create the binary variables for each value of race. So let's do one hot encoding. And to start off, let's do a proc freak on this dataset. Proc freak data equal to data dot hsb2 tables race. While I already know the number of categories and the value, it's always a good idea to do a proc free to check for the values that you have and there are no unexpected values. So let's look at the output. So instead of the HTML output, I'll just look at the text output much faster. So there we have the four values of race and the number of observations in each, the percentage observations. And I'm going to create a different column for each of them. So let's see, the coding for race is Hispanic is coded as 1. So let's do this. Data data dot hsb2 set, or let's me create a new variable hsb2 dot categorized set data dot hsb2. I'm going to create 4 new variables over here, or 3 new variables. Format race underscore Hispanic as a continuous variable. So let me say best 32 dot. Then I want to create format race underscore Asian as best 32 dot. So it's a numeric variable. Then I want to create another variable, format race underscore African American as best 32 dot. And let's create the values for this. So now I'm going to use an if then else statement over here, and let's say if race equal to 1, then in fact I'm going to set all of these values first to 0, so that by default they're all 0. So race h equal to 0, then race a equal to 0, and then race underscore a equal to 0. So if race equal to 1, then race h equal to 1, else if race equal to 2, so I know 2 derives for Asian, then race underscore a equal to 1, else if race equal to 3, then, and 3 I know is African American, so race underscore a equal to 1, and that's all I need to do. So I've created a set of variables. I'm going to run this. Let's hope there's no error. Look at the log. Yep, so no error, it's run correctly. Let's look at the data set. Let's eyeball the data set to see if there's no problems. And I've got these redundant variables over here, but that's fine, and there we have it. So let's compare it with the original values of race. So let me hide these columns. So for race 1, race underscore h is set to 1, everything other two variables are set to 0, and it's a best 32, so it's actually taking a lot of space, but I could have used only a binary variable over here as well, but doesn't matter. So wherever it is 2, Asian is set to 1, the two are 0, and wherever it is 3, it's set to race A is set to 1 1, and 4 stands for a white race, and you will see all the 3 values are 0 in itself. So what will happen is for 4, if I'm trying to capture 4 in the dataset, the value of 4 will be captured in the intercept itself. So I don't actually need to worry about race 4, because the intercept will automatically adjust for the value of race 4 over here. Now let's build a model which we started off with. So in our previous model we had used all of these variables, and the analysis that we did, let's have a look at the output and see the R square that we were getting was about 55%, and science read write social studies was coming in as insignificant, and the variance inflation factor was also very good, so we don't have to worry about correlation over here as well. So let's try and build this model again and bring in these 3 new variables that we've created and see if we can actually increase the R square of our model. So let's bring in science read write. I'm going to put in social studies as well, and then I'm going to put in race underscore h, race underscore a, race underscore AA, and let the VIF function be there because I want to check the variance inflation and ensure that we're not bringing in any collinear variable. And let's look at the result. So this is our latest regression model, and there we have it. Okay, this is the previous one, so let's look what happened. Is there an error? Yep, so there was an error. I am actually figured out what the error was. I am still referring to the old data set over here and not the new data set which I created. A rookie error. Let's fix that. Yep, and one must always check the log before one goes into it. So here's the log, and right now it's run correctly, and let's look at the result. So there we have it, and our regression is significant, and you can see the R square has jumped up from 55 to 57%. So uh, there is a little bit of increase in R square, but let's see if our variables have actually come in significant or not. So here are our variables, and I can see that the variance inflation is low, but let's look at the p-values. Race underscore Hispanic 0.85, and it doesn't seem to be significant. Race underscore AA again 0.60, it doesn't seem to be significant. But social studies has come down to 0.08. We may or may not want to keep it. So let's start removing the most insignificant variable first of all. So let's remove race underscore H. I want to remove race underscore H over here from here. So let's say removing race underscore H, and let's copy this, and let's race H underscore H go, bye bye, and running this again, and let's look at the latest result. So there 57% is still over there. Race underscore H we've removed, and I think race underscore AA or African American also has to go since it's not coming up as significant, right? So let's remove race underscore AA, and let's build the model again. So as you can see, while we've brought in race as a variable, it has not increased my performance so much as I would have expected it, but let's see nonetheless. So we're still 56%, so we're significantly higher, and race underscore AA has come in significant. It's on the borderline 0.03. It's still greater than sorry, it's less than 0.05, and I think it's time for social studies to go. So let's remove social studies as well. So I'm going to remove social studies directly over here. Sorry, let the trail be over there. So remove social studies, and let's get the model. So remove social studies, and let's look at our result. So 56% of the variation explained. All variables are significant except race underscore AA is coming at the borderline. So it's at 0.05 now. So as you can see, when I add and remove variables, the p-values of all the other variables also start wandering around. So while race is, if I put in race, only one category of race is coming up as significant in explaining the variance of math, and that too is coming at the borderline. So I may or may not want to keep it. So while we've tried to bring in race, and we've demonstrated in this video how you can create one hot encoding or binary coding, in this particular example, the categorical variable did not seem to help us too much. But we've got a lot of other categories also in our data set. So if I look at my data set HSB2, the new data set now, we have one more variable which I'm a little curious about, and which is the gender variable, and gender is already coded as a 0, 1. So instead of coding gender as male and female, the dataset already has 0 and 1, so I don't need to do 0 hot encoding. And since there are only two categories, I know if there are two categories, I need to create 2 minus 1, which is only one variable over here, and that variable already exists. So I can bring in female directly as a variable in our model. Let's see if it comes up significant in our regression. Adding gender to model. So let's bring this in. Add race AA, and I'm going to add gender. The gender name is simply female, and there we have it. Let's look at this. Okay, this is my previous model itself. Here we have it. So you can see while we brought in female, it did not help us too much. And if you remember, gender is not significantly impacting the math score as well. So if I remember the t-test over here, and we can show it as well. So does gender impact math score or not? So if I do a PROC t-test, data equal to dataset name, this class female. So you want to test whether female impacts math score or not. Var math run, and if I run this, I see that the p-value is 0.58. So female as a or gender as a variable does not impact the math score too much. So even if I bring in female, it doesn't seem to have any impact. So we know that that female is insignificant, or female or gender variable is an insignificant variable. We don't need this variable in our model. But for demonstration purpose, it was already in a binary or a one hot encoding format, so I could directly bring it in. Now what you can do as an exercise is that we've got some other variables also. I want you to try to build one hot encoding for socioeconomic background, which is 1 2 3, for school, which is 1 2, and for program, which again 1 2 3. If I look at my data dictionary, you will see that socioeconomic background is coded as 1 2 3 or high medium low. School is private or public school, and program is a vocational or your normal or training programs. So I want you to create the one hot encoding variables for all these three categories, categoric variable, and within each categoric variable, based on the number of categories you have, you will create n minus 1 binary variables for those, and then build a regression model with all the variables as your independent variables along with the variables we already have, and generate the VIF and start paring down variables. So remove variables which are highly collinear, remove variables which are highly insignificant, i.e. p-value greater than 5%, and then finally generate a model and see if you can beat the 56% variance that we've managed to bring the dependent variable explanation now. So the model that we currently have for math as the dependent variable, in this model we are able to explain about 56% of the variance in maths by using science, read, write, and race. So I want to try and bring in socioeconomic background, the type of school attended, a type of program as well into this model, and see if we can push it up. Let's see if we can get it to 60%, and I'll leave that as an exercise, and we'll come to that little later when we are talking about overfitting. So this was a simple exercise on bringing in nominal variables into my regression model.